All right, so we have already discussed the nature of collective excitations in solids, crystalline structures, and made emphasis on the fact that these excitations actually originate from the spontaneous breakdown of translational symmetry, which gets broken every time you create a crystal. The crystal itself breaks this translational invariance. As a consequence, there are some excitations called Goldstone walls, which we know as acoustic phonos, which try to recover this broken symmetry. Why? Because they show us that there is no energy required for a uniform shift of the sample as a whole. In the limit when k goes to 0, the energy goes to 0. That's precisely what is meant. Uniform translations don't require any energy input to make this translation possible. But nevertheless, these excitations, whatever is their origin, they exist. They form a continuum. This is very important. They fill a certain energy range from 0 up to the maximum typical energy, which is roughly speaking of the order of the Debye temperature divided by Planck's constant. And we would like to know a little bit more how these excitations show up in thermodynamics. There's a question, what is the low temperature behavior of the specific heat, which would be trivial if the system were classical. The specific heat would be just constant, but in fact it is not. It is strongly dependent on the temperature. Not as strongly as predicted by the Einstein theory, because the Einstein theory deals with independent oscillators, and any oscillator, any isolated oscillator, has an energy gap in the spectrum. There is the ground state energy, and there is a finite gap, h omega, to reach the next level. And this goes on. Every time you have a gap, and you place such a system with a gapped spectrum into a thermal bath, and you measure any quantity related to thermodynamics, you will get an exponentially small behavior dependence of this quantity if the temperature is much smaller than the gap. Because if this is the ground state and this is the first excited state, so let it be 0 and call this 1, the first excited state. This does not contribute to thermodynamics. The ground state does not contribute to thermodynamics. Thermodynamics measures temperature dependence of physical quantities. This quantity, this thing which is known as the ground state, does determine the ground state energy. If you have the Hamiltonian and you build up this diagonal matrix element, you can call it, this is the ground state energy. But this is not what you want. You want your system to get excited. The system, the participation of quanta is important not to be non-zero, not only in the ground state, but partially at the lowest excited level as well. And every time when you have a finite gap, call it delta. The probability of getting on the first excited level will be proportional to minus delta divided by T. And it's absolutely clear that the longest temperature is much less than the gap. This is an extremely small quantity. Therefore, in the Einstein theory, when there is a finite gap, which is proportional to the frequency of each oscillator, at low temperature, you have an exponentially fast decay, which is too fast to reproduce what people measure experimentally. Now we will try to improve the situation and take into account acoustic phonos. Now, as I said last time, and you know it well, that if you are in a three-dimensional crystal and you fix the propagation of the wave, some compression wave, whatever, in some direction, labeled by vector k, then you have two options. Either your displacement, u of k, is parallel to k. So in other words, the displacement follows the direction of the wave. It's very much like what we have in one-dimensional case. We have compressions and verifications just in the same direction as the axis. But because of three-dimensionality, generally speaking, you also have possibilities for the displacement which are perpendicular to k. And there are two such displacements, two independent, because there is a plane, perpendicular plane, and you can choose the coordinate system in that plane and therefore classify two types of such displacement. So in other words, you write down this displacement uk and also indicate lambda, which is the polarization index. And every time you expand then u of n, you have to take into account the existence of these different polarization vectors, and you write down something like square root of nm. This is more or less as how it was before. Now you add extra summation over n. You write down q lambda, which is the Fourier transform of the corresponding coordinate, but to keep this its vector nature, I have to put this unit vector ek lambda, and then I have to write down something like this, when RA naught is the equilibrium radius vector on the lattice. Well, for instance, which is, suppose n1 a1 plus n2 a2 plus n3 a3 on the simple, say, rectangular lattice, however you want. So these are just three vectors for each value of k. There are three such vectors, e1, e2, e3, mutually perpendicular. They form a triad. And these are necessary just to indicate the vector nature of this displacement and also take into account different possibilities for its polarization. It's not the most pleasant thing in the world to deal with. If you start doing these calculations, it's so boring, you know. I'm sorry, I'm just expressing my point here. I always prefer, if you have to explain something fundamentally, it's the right thing to do, to follow the advice of the great physicists, the great scientists. Simplify the problem as much as you can. And try to understand the essence of the problem in the most simple terms. Then when it comes to reality, and reality requires from you to take into account these things, knowing already the answer, it will be much easier to handle it. Right, so this is a very common thing. So, nearly along the same line was thinking the great physicist whose name was Debye. And who was successful in explaining many interesting observable properties of solids, in particular those properties which are related with lattice vibrations. And he invented the model. The model goes as follows. So generally speaking, when we have omega, we have to put a lambda here as well. We have to distinguish between different polarizations. First of all, I want to tell you one thing. How many acoustic modes, you already know it, because you have already had your course on phonons and electrons with Nadia Bingheli, I believe, right? You did. Okay. In the three-dimensional case, you have to have three acoustic modes. Three, just because of this lambda, three values of this polarization. the unit cell as a whole must be able to vibrate together with the coherently with the other unit cells in such a way that the Goldstone mode must be there. Rephrasing everything into our language, it is just not like that. The extra 2 degrees of freedom, extra 2 Goldstone modes, extra 2 branches of vibrations come from the fact that the substance is not one-dimensional, but is 3-dimensional. There are some displacements in the plane perpendicular to the axis along which the wave propagates. But at small values of momentum, you expect that your frequency is a linear function of the momentum. But the sound velocity depends on the type of the wave. For a longitudinal wave and the 2 transverse waves, sound velocities are known to be different. There's no reason for that to be identical. Right? Moreover, this is only true in this limit, but when you increase k, and now you have to use your 3-dimensional imagination and imagine a brilliant zone in momentum space as a 3-dimensional surface. Whatever that surface would be, it could be a cube, for instance, or maybe some more complicated figure. But when you reach the boundary, the surface of this brilliant zone, of course, this frequency will display the strong deviations from linearity, will curve, and reach its maximum value. Because this has to be anyway, has to be a periodic function, therefore it cannot be monotonous increasing linear function. So Debye said, no, I don't like it. It's too complicated, it's a mess. And it cannot be decisive. So therefore, his suggestion was, let us replace omega k lambda by omega of k, which is not a function of lambda, does not depend on lambda. In other words, at long waves, we have only one sound velocity, s, independent on the polarization. The same velocity for all 3 polarizations. Of course, it's a modal assumption. Simplifying mathematical trick, just to, maybe not too exact, maybe rough, but it works. You'll see. But it's not the end of what he did, actually. If I choose some direction in space, okay, say, I fix the direction, I call it zkz, for instance, right? And I know that for a small k, I have a linear dispersion just indicated here. Right? But then I also know that it starts curving and reaches some value typically at the zone boundary. Debye says, no, it's an excessive complication as well. It's too complicated as well. What shall we do? Let us continue the straight line and then cut it off and some characteristic value kd. And then nothing. Just the acoustic wave, just the Goldstone mode, which abruptly at some point stops. And then you have a discontinuity down to 0. We don't even bother about periodicity, nothing like this. Right? So what you have, in 3-dimensional case, you have 3-fold degenerate linear spectrum. It's degenerate, 3-fold degenerate. 1 longitudinal, 2 transverse. Right? But now there is a problem. How to count the number of allowed states? We have to remember that if we are in the brilliant zone, and m is the number of unit cells, the unit cell may contain more than one different atoms. The number of states on K states, momentum states, pseudo-momentum states in the brilliant zone coincides with the number of the unit cell. This is one of the theorems you must have learned already in the course of band theory. That's one of the basics of band theory. What about things happening here in this picture, in the Debye picture? Now, if you limit the allowed value of K by some maximum vector called maximum value KD, then you have a volume in momentum space, a sphere, if you wish, whose radius is KD, which forms immediately if I replace my brilliant zone by this construction. This is my new brilliant zone, if you wish. It's not the true brilliant zone, doesn't follow from any deep block theorems. No, just a result of my tour de force, I would say. I want it to be so, and I do it. Let us check a posteriori whether or not I'm right or not. So this is the volume in momentum space. What is the density of momentum space? We all know from the very well-known prescription that if we are summing some function phi of k over the first brilliant, over the brilliant zone, then they going from the sum to not necessarily over the first brilliant zone, over any volume in momentum space, then the passage from summation over k into integration goes with this formula. This is the density.
2 pi cubed.
Oh, yes. Thank you. Correct. This is the density of momentum space, momentum states, which, as you can see, does not depend on momentum at all. It's just a number determined by the volume, right? So you multiply it by L cubed divided by 2 pi to the third, and this has to be equal to it. This is done with normalization. The volume multiplied by the density of states, it gives you the number of states. The number of states within this sphere should be equal to the right number of, or at least to be of the order, if you wish. And that gives you a estimation KD turns out to be 1 over L, and here is 6 times P squared, and what? And the number of particles. Indeed, when I push it inside, what I have is n divided by L cubed, which is nothing but the density. Right. And if A naught is the lattice constant, then it is clear that KD is inversely proportional to A. That's all what we need. The number I'm not interested in, what is the factor, square root of 2, or P squared divided by 8, doesn't matter. So this is the Debye construction. So therefore, once and for all, we will use the linearized spectrum for the phonons, replacing them by the acoustic phonons. And then we would like to calculate the energy, the average energy as a function of the temperature for a 3-dimensional crystal. How we do it? We write down this is the summation over k, summation over lambda, h omega k, lambda generally speaking. And here I have the average occupation number plus 1/2. So what did I do? I simply wrote down the expression for the energy of the non-interacting photons, summing over all of them and over all polarization of those, and averaging here. Well, the average of any quantity, average, is assumed to be a thermal average within the ensemble. For instance, if I have something like, if I label by mu any state, then what I need to do will be, okay, well, let me put it like in the standard form, rho f, trace rho, when rho is, that's it. Or otherwise you calculate the free energy, it doesn't matter, it's just the same. There are millions of ways to do the business. Now, this one-off, as everyone knows, this originates already from the very well-known expression for the energy of a single harmonic oscillator. This is the contribution of the zero-point motion. This is what makes the difference between classical and quantum oscillators. Even in case when n average is 0, even in case where the number of phonons is 0, where the number of excited quanta is 0, there is a finite energy. It's amazing, right? It's a classical thing. In classical physics, it would be absolutely unimaginable because the ball would be lying peacefully at the bottom of the potential well without any motion, immobile, at rest. That's not so in quantum physics. So this piece obviously is a constant, and therefore it doesn't contribute to thermal energy. The thermal effects appear from, originate from here. So therefore I can immediately, being interested in the end of the day in the specific heat, I can build up the difference this is the zero temperature value of the ground state energy, which is determined by 1/2. And therefore, the result will be now what I'm doing. Look, lambda is a dumb variable. It doesn't enter any expression. It gives me simply 3. Right? Summation over k, it gives me the volume divided by 2 pi to the third. 3-dimensional integral over momentum space. Under that condition, then the absolute value of the momentum k is less than kd. I'm restricted with the device field. What is this? This is a thing which is very simple. This is 1 over what? H omega k. I will temporarily write it down like this, like divided by t minus 1. That's fine. But now let me continue. So this is 3 L to the third. You can keep writing V, you can write down L to the third.
Shouldn't we be using the H bar omega also in the integral?
Well, we will be using H bar, or we will not using the H bar in the end of the day. Well,
Yes,
it's kind of, why are you asking that?
No, the average of n is the Bose distribution, but the omega k, shouldn't we be using it in the integral also? Because it's just...
Omega k is just that very omega k which is here, which I ignore simply the dependence on lambda. I say that the 3 branches are degenerate and constitute only 1 branch. They don't depend on lambda, right? Whatever remains as the dependence on k, which is given by the Debye formula. It's acoustic formula, nothing else. What the essence of the question? I don't understand.
How to say?
You are unhappy that I'm writing H or
No. I'm unhappy because we are only integrating the Bose distribution without omega k in front, which we have in the summation.
We are, wait a second. We are summing over k.
which we turn it into an integral.
We are averaging over ensemble.
Yes.
The average over ensemble of this object
Is this
is
expression?
the Bose distribution function,
Yes.
which is written here.
What about omega k in the summation? This one.
Ah. You should have said more aggressively because you started very politely and led me to somewhere else because well, into the gardens of music, whatever. No, it's a stupid mistake. You must have said you have missed the turn. That's it. Here in the West, we experience a shortage of time. We live in such a way. Hard. All right. Yes, correct. So integrating over the angles gives me 4 pi. 4 cancels 8, so here I have twice p squared. I'm just doing things which I should not have been doing, but nevertheless I do them. Let me put it like this. I integrate it over the angles. Here I integrate from 0 to kd, dk, k squared, the 3-dimensional integration, right? That's from here. Now from here, h s k divided by e, h s k divided by t minus 1. If this is correct, thank you. All right. Now, the thing which follows immediately goes like this. So, I want to have an object HSK, if you wish, right? So for this, I write down this, so here I write down in the denominator h to the third, s to the third. This is coming from here and 1 linear from here, as far as I can see. And I've introduced the epsilon, which is h s k, or simply omega, if you wish. Something like this. Then I have from zero to the upper limit will give me h s d by vector. d omega times omega square once and one more, third. And the exponent omega divided by t minus 1. Now I can kill this and write down square and things like this. All this is just a trivial bookkeeping. The last transformation is obvious. I have to introduce x, which is omega divided by t. And as a result, I will find out that delta E is a function of t, skipping all the other coefficients and prefactors, will be proportional to, coming from here, the fourth power of temperature, 3 from here, 1 from here, and the integral from 0, now the upper limit, look at this quantity, h s k b s h omega d, which can be called the Debye frequency. And all this is known in the literature as kb Debye temperature, which is just the same. Right? So the higher possible value of the frequency is called the Debye frequency. And you can rephrase it in terms of the Debye temperature. H omega is the same as kBt, kb theta. Right? So therefore here what I have is the ratio, the Debye temperature over the temperature, x to the third, dx at the center. Now comes the observation. So the temperature enters two places, here and here. But you are interested in the low temperature limit. This is quite obvious because the all construction, all derivation by Debye was aimed just to calculate the thermodynamics at low temperatures. Because at high temperatures it would be kind of suspicious. All these approximations are questionable at temperatures of the order of the Debye frequency. But they will be just well justified, or more or less well justified, at low temperatures. So therefore the ratio, this ratio, the upper limit is a huge number. And at large values of x, the integrand, the function which you see, observe, inside the integral is exponentially small, becomes exponentially small, because at large values of x, this is the most important part, and goes up with the exponent minus x. It cuts off the integral. So therefore you can, without any hesitation, say, if you replace the upper limit by infinity, the error you make is of the same order, of this order. You lose an exponentially small correction. I leave it to you to prove it. But it's already obvious. What remains here is a number. It's p to the fourth divided by 15, if I'm not mistaken. It's a number. So all in all, the energy turns out to be proportional to t to the fourth, and the specific heat, which is derivative, is this. As the French would say, voilà. That's all. That's the derivation. Now, what behind all this? What behind all this is the very existence of Goldstone modes. In other words, of the acoustic waves. We do not have a gap between the ground state and the first excited state. This gap is microscopically small. Is it clear why it is small? It is small because if you quantize the momentum, remember how you quantize the momentum. It is like this. This is the typical distance between the momentum, right? And your frequency is proportional to momentum, right? So therefore, if you take the value omega equal to 0, which would correspond to the ground state, the first non-zero value would be proportional to S divided by L. For a long system, this is a small, very small quantity which disappears in the thermodynamic limit, which closes. Only in finite systems you have these microscopic gaps. But in the thermodynamic limit, it closes completely, and you have a branch of collective excitations, a continuum. Because of the existence of this continuum, because of the fact that at any finite value of the temperature, you do have excitations which are below in energy than this temperature. This means that you have a contribution. And this is why this contribution is not exponentially small, because of the absence of the gap. Every time you have a continuum, you will have power loss, and that's one of the cases. Whereas in the Einstein model, you have an exponentially small. That's all. This is basically it, actually. This is all we can tell about the role of Goldstones. Of course, it's not completely exhaustive. There are still other effects. But to us, this example is an important manifestation, which proves the very existence of the low-energy modes, such as acoustic phonemes or Goldstones. Well, now, if you have some questions, any questions here? If you have any questions. So now we come to a more fundamental question, if you wish, and a very curious observation we're going to make regarding the role of dimensionality. First of all, we have to make sure that the path we have chosen is self-consistent in a sense, in a way. What we have said was the following: let a crystal exist. Now we consider it small vibrations. In other words, we, first of all, what we assume, what we didn't say, didn't spell it out, whether the crystal which allegedly exists is stable. Against what? Against excitations which are present in this object, right? Our main assumption was, as you remember, that once we have created a crystal, the deviations of atoms from their equilibrium positions, displacements, if I have R of n, and then I subtract R of n0, which is the equilibrium value in the crystal, and I call it U of n, this quantity is supposed to be much less than the very spacing given at any moment. Well, of course, by symmetry, the average value of U of n is 0, but the average of U1 squared is not. So therefore, I can require that U1 squared divided by A0 squared should be much less than 1. This is what I have to prove. If it turns out, like what is written here, okay, I would say the lattice is stable. If it is not, then we have a problem. Then we have to think how to avoid the complication. Let us start moving in this direction. Now let us start from something very simple. Let us start from the single isolated harmonic oscillator. And in the harmonic oscillator, there is a notion of the quantum length, as you remember, right? Which is defined as square root of h divided by m omega. M is the mass of the oscillator, omega is frequency. And the whole construction is, I'm sorry. I would expect you to comment that you didn't say a word.
Didn't see.
Yeah, so this is the quantum length, which formally disappears when h goes to 0, which is good. We know the origin, we already discussed it. And this length, roughly speaking, gives us what? Gives us the extension of the wave function in the ground state of the harmonic oscillator, which gives us, roughly speaking, the order of magnitude of the amplitude of zero-point motion. So this is the uncertainty. This is the uncertainty of the location of the oscillator in the vicinity of this point. Right? Now, we have crystal. Suppose we still maintain this estimation as if we have a set of more or less disconnected harmonic oscillators, even though it is not a good approximation, as we already know, because of the existence of the collective excitations, but very roughly, something like in Einstein model, right? In the spirit of Einstein model. Suppose that I keep this estimation for each particular atom. But on the other hand, since I'm in a crystal, I have a new object, new length, another length, the length which is a feature of the ground state. So this is the quantum length which characterizes vibrations of each harmonic oscillator. And there is another length which describes a structure of a much larger scale. Right? Let's compare. Right? So let us find out what is the ratio of psi squared divided by A naught squared. It will be H, it will be M, omega, A naught squared. Right? Now what we can do here is the following thing. So we can, there are several options which we can follow. We can write down H squared divided by M A naught squared and divided by 1 over H omega. This is what we can do. Right? This is one option. Okay, yes. So it's intuitively clear that to ensure that this ratio is much smaller than 1, what you should expect, this is roughly speaking the order of magnitudes for the kinetic energy associated with the zero-point motion. You delocalize, it's not exactly the zero-point motion. The zero-point motion is this. This would be like okay. If I had taken an side and put an atom here there, and allow the momentum to have an uncertainty 1 over A naught, when the A naught is interatomic spacing, which is roughly speaking the order of magnitude of the wavelength of the future excitations, collective excitations, then this appears to be as the ratio of the kinetic and potential energy. Very good. Right? And if this ratio is much less than 1, then you can say that quantum effects are small. Why? They should be small. They should be small for the very simple reason. The crystal, any kind of crystal, is a classical object. It's a periodic arrangement of self-assembled atoms in space with well-determined, well-defined coordinates. Such picture has to be classical. There is no such a notion. No, there is such a notion as quantum crystal. There are some quantum crystals which are periodic, but whose lattice size, the number of lattice sides, is greater than the number of atoms. It's a very interesting object. You understand, right? You may say if you take some atoms away and put them in the pocket and throw them out, then you also have some defects, some vacancies. No, there's no vacancies whatsoever. The number of atoms, the number of matter per lattice size is less than 1. It redistributes itself, so it's quantum. It behaves like a wave. Such things have been discovered. It's a very interesting part of condensed metaphysics. For some reason, in last years, not much attention has been paid to that, but it's what was a very interesting thing. No, here everything is fine. Here everything is fine. There is one more way to look at this ratio. This is one thing which more or less keeps you happy. Ratio of something which is related to kinetic energy or potential energy. The slow system, yeah. On the other hand, you can play the following game. You can do such a thing like you write down psi, which is h times A naught. Here we have a mass, and here we have S times A naught, 1/2. Okay. Why is it? No, there is no S. Omega. I'm sorry. Omega. Now I may say that omega can be a very roughly estimated like KD by S, which is S divided by A naught. So omega times A naught turns out to be S. Omega times A naught plus S is H equal to A naught. And S. That's good, 1/2. And now I will build up this psi square over A naught square again, but with slightly different notations. It will be H A naught and S. This goes down, right? I will write down now S here and S squared divided by A naught. This is the same as KD. And what we have found here is theta d1 divided by m squared. To me, this representation is more acceptable physically in a sense because you can see what you are comparing. In the second case, however, the expression is more compact because it represents a ratio of the Debye temperature and the average kinetic energy of a particle which propagates. You have to imagine an unimaginable thing. The particle which propagates with the speed of with the sound velocity. So imagine that you have sound propagating across the radius. You see what I did here? I just only order of magnitude estimations. Now nothing by that. No true calculations. Only order of magnitude estimations. It is clear that theta of V is the quantum object, not this one. This kinetic energy has a strict mimic in classical physics, of course. It's kinetic energy. But this is the Debye frequency. The Debye frequency has its H in its definition. Therefore, it's a quantum object. So as long as quantum effects are small, as long as theta Debye is small, then the ratio psi squared divided by A naught square is small, and therefore you expect that the zero-point motion, the radius of the zero-point motion doesn't exist. It doesn't exist. It's much smaller than interatomic distance. It's a good criterion. Another option would be just to increase the mass. Playing games with heavy masses. The heavier the mass, the better for classics. Light masses oscillate fast. Fast oscillations means that quantum effects will start dominating. Right? So this parameter is the parameter which would ensure, from a priori considerations, stability of a classical crystal. If this inequality is satisfied, you expect that everything will be fine. Let us check it using more reliable calculation. Now again, I will not follow the precise definition of the lattice displacement because it contains lots of unpleasant things, even though they are quite necessary. There's nothing dangerous in all this. But what I can immediately tell you that a very simple calculation shows that UN squared turns out to be 1 over nm. This follows from the standard definition. You sum over k, you sum over lambda, generally speaking, and here you have this q k lambda modulus square average. And this is valid in any dimension, actually, because summation over k may cover any space, any dimension. Here comes now the main observation. How should I represent qk lambda? I should remember that, in fact, everything we've done so far was successful because we used a very powerful formalism of second quantization. So therefore, we know that this is nothing but the normal mode, the coordinate in the normal mode representation, right? Under quantization, this k lambda transforms to an operator, and this operator has such a prefactor it would also have this mass, and therefore this prefactor would be simply similar to the characteristic quantum length, and what we write down here is a k lambda plus a minus k lambda dagger. And that's actually all to what we have. This is nothing but the direct translation of what we all know about second quantization of the standard harmonic oscillator in 1D and the problem of lattice vibrations, because the problem of lattice vibrations becomes similar to a problem of single harmonic oscillator due to the normal mode expansion, because normal modes parameterized with different Ks don't talk to each other. Now I take this modulus squared average. What will I get? Let us see. It's a simple thing. Now I have a k lambda a, okay, I'm sorry, the first term will be dagger. A minus k lambda times a k lambda plus a minus k lambda dagger average. It is absolutely clear that any averages of this kind are equal to zero. Why? The answer is correct, but who can tell me why?
Because those kind of operators form states with, like, how to say, different states have to. We have to take the scalar product of different states, which are orthogonal to one another.
And what is the difference between these states?
The number of excited.
Correct. That's right. So if you calculate the average of this kind, you have to remember the following thing, that when A acts on some state here, call it n, right? It will give you a state proportional to n minus 1. Now, on the other hand, the state A acting on the bra is nothing but the conjugate of A dagger acting on the bra, right? And therefore, it will give you a state n plus 1 conjugate, which is nothing but the bra state of n plus 1. And therefore, the main matrix element between the diagonal terms here, the matrix element, and n will be effectively proportional to n plus 1 and minus 1. This is what your colleague had in mind, I believe. Well, you may also say the following thing. You may even forget, quite legitimately, temporarily about second quantization, and say, okay, this is a quadratic form. I know that the Hamiltonian is always a quadratic form. It has structures like this, maybe even like this. It depends on the choice of representation, but it's always a occupation number operate. A dagger A, not A, not A squared, not A dagger squared, A dagger A. So therefore, if the Hamiltonian does not couple A to A or A dagger to A dagger, the corresponding averages have to be 0. Only those averages are not 0 whose corresponding operators are present in the Hamiltonian. This is a common rule. So irrespective of whether the problem is quantum or classical. So, fine. So therefore, we only worry about this term, no, these terms, and this give us h twice omega of k. Here we have nk lambda, right? Plus, here we have a dagger, but we know that A and A dagger satisfy the following algebra. The commutator is this one. Therefore, I can write down, understanding this should be, okay. All right. Plus n minus k lambda plus 1. That's the answer. That's the answer. But since we plug all this expression into k and minus k enter with the same, I would say, weight, you simply double the coefficient here and n plus 1, and then you push 2 outside and you get n plus 1 half. So the final result looks extremely simple. Is un squared is h, is the n, is n, sum over k lambda, 1 over omega k lambda. Well, I can remove this lambda, after all, doesn't need it. And k, again remove lambda, plus 1 half. That's the expression of the average square displacement. Well, what is written here is the number of phonons, which goes to 0 at 0 temperature. At 0 temperature, we don't have phonons. But we do have this piece, our beloved piece, 0-point motion. Which means that we can ask the most important question before we switch on a finite temperature. Suppose the whole system is at 0 temperature. Then the only motion which is there is the 0-point motion. What is the contribution of the 0-point motion? Can it ruin the long-range order, the crystalline order, or the crystalline order survives 0-point? It's a good question. So therefore, we can, in the first approximation, forget about finite temperature and do all calculations at 0 temperature and ask yourself whether our lattice is stable at 0 temperature. Yeah. H is there. All right, okay. So what we have for the 0-point motion, we have un squared. Well, suppose the dimension is 3. Then we have this 3 all coming out of the polarization. H is here. Number of particles, the mass of particles, some oscillation over k, the L to the third, 2 pi to the third, 1/2 coming out from here, neglecting the averaging Ka. Instead of summation, writing down the integration d3k. K absolute value is less than Kd. We're again maintaining the Debye model. It's quite enough for us. And what remains is our denominator, which is 1 over S and modulus of K. Modulus of K. So, now if you are after all the numbers, let us do with the numbers if you wish. 3HL to the third, 4 pi from here. So it will be 4 times pi to the third. Is it clear? Is it 4 pi, 4, it's 8, 4.
Pi cubed.
4. And then pi to the third, and 4 pi coming out from the integration. So it should be pi squared. Correct? Correct. S comes out from here. Integral from 0 to Kd. K squared dk divided by K, K dk. So all in all, what we have, removing all what we don't need. I forgot N, I forgot N. And you keep silent, by the way. There are some people very, very attentive. Skipping such serious things and without producing any noise. Just all right. Okay. So, all right. L cubed divided by N is what? What is that? It's A naught to the third, right? It is clear. The mass is here. 3 and P squared I'm not interested in. MS is here and Kd squared is here. Right? Right. Let me do the following. I will write down A naught to the third. Just a second. Kd, we know that Kd times A naught is on the order of 1. So therefore, here I have A naught. Here I have M. Here I have S. Where is H? H must be somewhere here. Fine. And now I build up 2n squared divided by A naught squared. And then I have H, and I have M, S, and A naught. I keep going. I understand that this is H, Kd, MS. I multiply by 1s here and in here as well. And here I have divided by ms squared. That's precisely what we have. This is how it is derived, honestly. And in three-dimensional case, there is nothing else but only the numbers. Pi squared in the denominators, 3 and whatever numbers, which don't matter. So our conclusion was correct. For a three-dimensional crystal, once this condition is satisfied, once the quantum effects are small, the classical ground state is stable. And the phonons represent well-defined quantum excitations over the classical ground state. By the way, we will have something similar starting from the next lecture, because we will turn to magnetic systems. There too, for instance, for a ferromagnet, the ground state will always be classical, but the excitations will become quantum. So far so good. So you would say, is everything's fine here? Can we be completely relaxed and say that the crystals can exist, but what about other dimensionalities? Remember, in the very, very first lecture, and I was referring to main trends in contemporary condensed matter physics, such ideas like more is different and things around that. One of the key points which was introduced was the notion of universality. And there was a statement that tiny details of matter on microscopic level are inessential, are not essential, are not important when we lower the temperature and look at the emergent properties. What is important are the so-called gross features, which are based on the notion of space dimensionality and the symmetry. We do nothing bad with the symmetry, but dimensionality is at our disposal. This was the case, d equal to 3. I leave it to you to do the same for d equal to 2. This will be your homework. But let's now check what happens in one dimension. So far, all our consideration was one dimension. Our models were basically, except for maybe today's lecture, was one dimension. It immediately follows from here. In one dimension, instead of d3k, it's just simply dk. dk divided by k is a logarithm, I'm very sorry. So let us do this calculation more accurately. Let us start from here. No, we can't start from here. We should start from here. In 1D, un squared. I will only write down main parameters. Planck's constant is important. L, the first power, is important. And M, everything is important so far. And here I have 1 over S going out here and is present here. And this is the integral dk divided by k from the maximum value is kd. Let us temporarily write down the minimum value, although we are not so much aware of what is that. If there is some minimum value of momentum, the integral is a log of kd divided by k minimum. And in the previous case, in the three-dimensional case, without any hesitation, the lowest available value of momentum was 0. But if I take 0, the logarithm is divergent, and we are in a very, very big trouble. We have a divergent square displacement. Not simply large, but divergent. So first of all, we have to remove divergences, because there is no room for divergences if we are consistent physicists. There are no divergences in finite matter, right? So there's a kind of problem with calculations. We're doing something we're doing not in the right way. For the question we should address is, since we start with a finite sample, what is the minimal value of the momentum for a some finite sample? There is no k equal to 0. Because k equal to 0 means that the wavelength is infinite. When the sample has a finite length, the infinite wavelength makes no sense. So therefore, when you quantize the momentum in the box and write down that kg is 2 pi divided by L, and g1 and g, as we believe, is 0, plus minus 1, plus minus 2, and so forth, please be so kind, throw out the 0. There is no such a thing as 0. If the length is finite. So therefore, the minimum value of the momentum is 1 over the L. This already follows from the, if you wish, from the uncertainty principle, or general principles of the Fourier transformation. Okay, then this logarithm transforms into a logarithm of L KD. But we remember that KD by the order of magnitude is 1 over A naught, where the A naught is the Ricci spacing. And we also remember that L is n times A naught. So therefore, it is log of n. This is what it is. It's a logarithm of the number of lattice sides in a given lattice. It's a finite but huge number. Huge. We are still in trouble. Why? Let us do a little bit better job. Let us build up the object, which is U squared divided by A naught squared. If I repeat everything just as we did before, we will find out the following thing. It will be some number, just a number, 1, 2, 3, P, whatever. The ratio D by temperature divided by MS squared. This is our small parameter, that very small parameter, times the log. Call this parameter G. So you have this ratio G times log. A small number times a large number. And God knows what is that. Now, one thing is absolutely clear. We are in a fundamental trouble. Unavoidable. Uncurable. Why? Because you only are entitled to keep the volumes or the particle numbers for extensive thermodynamic quantities. Additive, like energy, momentum, free energy, entropy, whatever. But there are also intensive quantities, which are not proportional to the total particle number, such as densities, compressibilities, susceptibilities. This is one of those. Look, what we are calculating here is the average square displacement of an atom in certain units. In certain units. It should be equally valid for a system with number of particles 1 million, 1 billion, or infinity. This is a microscopic characteristics which reflects, however, the properties of the system over all scale. Because all the goldstones are there. You see, all the goldstones contribute. It's again the same story about the goldstones. We are calculating something local, but determined by the spectrum of collective excitations at large distances. A very non-trivial fact. And it turns out that if I quite consistently, as a consistent theoretical physicist, for this non-extensive quantity, set n equal to infinity, in other words, go to the thermodynamic limit, I have a divergence. Conclusion is, there are no stable, in brackets, in the thermodynamic limit. There are no stable, in the thermodynamic limit, one-dimensional crystals in nature. They simply don't exist. So therefore, whatever we have done was done under assumption that this is a kind of caricature, if you wish, of the true or more realistic two-dimensional or three-dimensional world. But strictly speaking, now is it completely hopeless to deal with such a problem? The answer is no. And the answer comes from this condition. This is small, and this is large. When the one-dimensional crystal makes sense, when this quantity is much less than 1, this gives me a restriction over n. The log of n must be much less than 1 over g, or n must be much less than exponent 1 over g. Or the length of the system must be much less than some critical length, which can be estimated as a naught and 1 over g, which is much, much greater than a naught. It's a huge length. As long as my sample is shorter than this length, I can approximately speak of quasi-long-range order. There is no true long-range order, but there is a short-range order, but well-defined. And for samples whose length is much greater than L and so on, you have to change the gear and forget about your problem. Now, what you could and what you should do, actually. It is intuitively clear that if the zero-point motion already the picture, the degrees of freedom present at zero temperature, the quantum oscillations, the zero-point motion is nothing but quantum oscillations, already ruin the crystal, ruin long-range order. The temperature only adds to that. If you switch on temperature, it will only simply destroy long-range order even faster. Because quantum fluctuations are already destructive and thermal fluctuations only add to that. But there are situations when you are, for instance, in 3 dimensions. What we did today, we considered only the role of zero-point motion. You are most welcome to sit down and calculate what happens when the temperature is finite. Suppose the temperature is finite and low, much less than the d/4 temperature. What is the role of thermal fluctuations? So you cannot restrict yourself with only one term in the average energy. You have to take into account the finite number of phonons excited at a given temperature. The stability will look a little bit worse than it was at zero temperature. But will not be desperately bad. You will find out that the 3 dimensions, under quite plausible conditions, the lattice survive. Not both quantum and classical fluctuations, some semi-classical fluctuations. Well, what about 2 dimensions? In 2 dimensions, perhaps you will be able to immediately prove that everything's fine. That at zero temperature, the 2-dimensional crystal is stable. But we will also observe that at any finite temperature, at any, however small, non-zero temperature, your crystal, your 2-dimensional crystal, your 2-dimensional film will start melting. There's no such a notion like a 2-dimensional crystal. You know the story about the graphene? Have you ever heard about it? What the graphene is? Is anyone who doesn't know at all about graphene? Okay, I'll briefly tell you what the graphene is about. The graphene is a substance made out of carbon, which has a hexagonal structure, honeycomb structure, honeycomb lattice. Everywhere on the sides we have C. And you cover with this pattern the whole surface. And then you cut off and you have some kind of piece of material. And this material is called graphene. It is a monolayer. The thickness is 1 layer. 1 layer. You know how it has been made? You take a scotch, you go to the shop and buy scotch. And now you tear off the carbon, and then you look, and then nothing remains here. You can't see. Then you put it under the electronic microscope and see it. And you prove the existence of a single layer. 1 layer. Can you imagine? Fantastic. Nobel Prize. Yeah. Now, the way they manipulate for this, they have a substrate looking something like this. They fix the location of the endpoints here and here. They feel bending under gravity, a little bit like this, is located here. It's a two-dimensional discrete surface, modeling. The immediate question is, how can it be that it doesn't? It survives fluctuations because all the measurements is done at a finite temperature. You know the answer? The answer is amazing. It's amazing. It should not exist because at any finite temperature, according to the theory called Mermin-Wagner theory, two-dimensional crystals have no right to exist. But the system is smart. If you look at the profile of the surface, right, it should look like a line. As long as it's lined in cross-section, it's two-dimensional because this is the plane. What it does the following thing. It creates ripples. And then these ripples start interacting to each other. And every time a ripple appears, the system goes beyond the second, the 2 dimensions into the 3rd dimension. It becomes 3-dimensional. See? As long as you are, when I said, when you have a 1-dimensional crystal with atoms located here, forget about transverse motion. It doesn't exist. Your space is 1-dimensional Euclidean space. Here we would say, okay, this must have been a 2-dimensional Euclidean space. Not true. The experiment is done in the lab, which exists in a 3-dimensional space. So the film behaves according to the spec. It takes advantage of the existence of the 3rd dimension and stabilizes its structure by creating those ripples, which behave in such a way that the whole structure turns down. Then I don't know much in detail, but I know that philosophically it's quite acceptable and very, very appealing, because the system avoids 2-dimensionality by creating those defects of the structure. So please check whether or not the temperature is so destructive of 2-dimensional crystals. So this is one of the examples how important dimensionality is. In magnetic systems, we will have many more, even more impressive examples. For today is everything but questions, please. If you have. No questions. So, after lunch, I think you can move directly to.
We got it on email. Yeah. They sent it.
They sent it by email. Okay, by email. Okay. It's more or less. Okay. So on Wednesday we are getting together at 4 o'clock.